So we continue from yesterday along our path on the way to understanding what synthetic aperture radar is. So today we're going to really get into it, and pretty much all day we'll be talking about synthetic aperture radar. Again, today will be sick of it. So anyway, we're starting fresh now, and we'll start with principles. Okay, and we're calling some linear array principles in there to try and figure out where this synthetic aperture actually exists and how we can exploit virtual arrays to form a fine beam. And then we go through a technique, a signal processing technique that is able to form psi images with the acquired data from the coherent radar. We'll see how we can form images using this strip map technique, which makes use of this coherent integration technique as well. Then we look at another technique called range Doppler technique. The chirp scaling, we'll skip it for now and see if we have time. We'll do it later because it's a quite long and mathematical one. And then we'll go through a very important part, which is the system design. SAR works, try to make it work. We have to make sure that a number of parameters are really tuned in a suitable way, otherwise things don't work. And we'll try to understand how all this is related to these items here. We'll go through our system design example as well. Some sort of tutorial if you want, where you have to calculate some of these parameters and make sure that all these items are taken into account. And then we finish off with some multi-looker mode to defeat speckling. Speckling is a typical noise that appears in SAR images. We'll learn what it is and then how to deal with it. And the last part will be scan SAR mode, which is another mode for forming SAR images when very large swaths are required. There'll be also a practical session in between here. Right, so there's quite a lot to do today, so let's move on, and we start with principles here. And let's see, first of all, okay, how the geometry works and how we are trying to form what we call a synthetic aperture radar. So what we want to do is to improve, okay, azimuth resolution. So a single antenna, okay, may have this azimuth beam width, which is pretty much determined by the size of the element antenna. Now we think now, okay, of having one single element, right, mounted on a platform that moves along some rectilinear trajectory, okay, and as it moves, okay, this antenna sends out pulses and receives echoes. So we assume we have a radar attached to this antenna that is operating in pulse mode, and it's a coherent radar as well. So we assume that this radar is going to be switched on at some point here and switched off at some point here. What we're trying to create here is some virtual beam, okay, azimuth beam, that is much finer than the one of a single element, and it basically can isolate a small region on the ground with a certain, okay, azimuth resolution. So basically we want to form a virtual beam by coherently processing all the signals that are collected during all this flight from here to here. Okay? So as you can see, this is signal processing, because what I'm doing, I'm collecting data and I'm processing through to obtain something. Okay, the system itself is still composed of a single antenna. This antenna is moving along this trajectory with a constant velocity, okay, that we can set. Right, so what we want to do basically is isolate, in the sense of focus a beam only on one particular scatterer that is positioned in this particular geometry, the origin of this axis here. So this axis here, x, right, indicates the azimuth. So what I'm thinking of is now some sort of trajectory here. This could be trajectory of an aircraft, of a satellite, but also on something on the ground. I could mount an antenna on a car roof, okay, and move it. Doesn't matter. Now, I don't want to depend on a particular platform here. I'm just saying that this antenna is actually carried by some platform and is moving along a rectilinear trajectory. This trajectory here is parallel to this one, so the antenna is moving along the azimuth direction. Okay, so that means that now this direction here, which is the azimuth direction, is the same direction as their one. These two, of course, okay, differ only because of the distance between the two parallel axes. And this distance here will be characterized by a certain value. Okay, that depends on the distance from the platform to the actual point O, when the platform is in the center point here. See? Okay. Right. If this is our goal, right, and if this is the way we operate, then it means that if I transmit a pulse every TR seconds, and I'm traveling with a velocity v, I have virtual elements of my array. As you can see, these are virtual elements of my array. I don't have an array because I only have one element. But in time, in the time that it takes to go from here to here, I will build an array of n elements, okay? And these n elements are spaced by a delta u, if you want, okay? That is equal to v times tr, okay? So I get a number of elements here, virtual elements, so that I can create an array here, a virtual array, with n elements equally spaced, okay? Now, I have to make an assumption to basically state that this virtual array is equivalent to a real array. And what's the assumption that I have to make? The assumption I have to make is that whatever is illuminated here, that I call this the illuminated scene, okay, has to be stationary within that time. If nothing moves, if everything is stationary here, the fact that I'm collecting this signal at different times, or I'm collecting it all together with a real array, doesn't matter. If nothing moves, everything is perfectly still, time doesn't matter. Okay? Time matters when things change. Otherwise, it doesn't matter at all. I can take this measurement now, this in 10 years, this is in 100 years, and whatever. If everything is still, nothing changes. Okay? So this assumption is important, and it stands at the basis of synthetic aperture radar. The goal will be constrained to forming images of stationary objects. And that's what synthetic aperture radar does. Okay? It's good at forming images of stationary objects. If objects move, all right, things don't work. It's almost like trying to take a picture with your camera, optical camera, using a long exposure time of a subject that moves. How is that photo going to appear in your opinion?
Hello?
Good. But if you take that picture of an object that is perfectly still, you can even integrate for days, okay, that photo will be perfectly focused. So the concept is exactly the same. In this particular case, we have an almost perfect analogy between what happens with a radar and what happens with an optical camera. Typically, with optical camera, the integration time is a lot of light. It's very short, so you can even take photos of people that are moving. They don't move too fast. But everything's relative, right? So that motion has to be considered neglectable in that integration time. Now, to go from here to here, it might even take seconds. Okay? We'll figure out what these parameters are later. Later we will. And I can tell you this can be seconds. So within a few seconds, right, things have to be stationary. That means if you have a car moving here or a ship illuminating the ocean, that particular target will not appear focused. Okay? Good. We'll learn how to deal with moving targets. That's why ISA comes in, but that's for tomorrow. So for today, we stick with stationary targets. So in this particular condition, right, we are trying to basically build this equivalence between a virtual array and a physical array. Okay, so how we do that? We use a real antenna here with a poor azimuth beamwidth, sorry. Okay, so say something this large. This illuminates a large patch of length L. So this is from here to here is L, which is the same from here to here. Okay. The radar moves from here to here in a straight trajectory with a certain velocity. Okay. And we record all the echoes that come from these positions. We assume that the speed of light, okay, is much faster than this velocity here. In these conditions, basically, when I transmit and when I receive, I can consider this point stationary. This condition is called stop and go condition. It's virtually like you're moving here, you're taking a snapshot, move here, taking another snapshot, here, taking another snapshot. It's not really like that, but the velocity of the electromagnetic wave compared to the velocity of the pattern is so much larger that you can assume that that happens at the station. Fine. So you record all the ground echoes at all these positions, so you collect the data out of all these points here. And then you basically use signal processing, use coherent processing. So you add up these values here to form your focused beam here. So we basically use array processing to form this beam at broadside, okay, that actually is illuminating this point here. So if you, I don't know why it comes out like this. My computer is perfectly fine, and you run it on Windows and it comes out like this. Alright, so these are all tilde signals, which means that they're baseband versions of the received signal. Okay? So this notation here indicates the signal that we receive by the nth array element, so one of those, from an angular direction theta with respect to the length range. So theta is this angle here. And this is the signal that is received by the omnidirectional antenna for n equal to 0, which is this signal here. Then, if you add up all these elements here, from here to here, you get this particular signal here, which is the coherent sum of all these signals for a particular area theta. So this becomes a function of theta, of course. Now, if you write down the ratio between this and this, you come up with a so-called array factor. The array factor indicates the array gain So whatever you gain in terms of using multiple receivers, okay? So what happens here is when you add up things over a certain angle, you are basically summing up all the contributions, okay, that are coming from a particular direction. So this is coherent processing. It's like you're adding up the energy that you receive in the first element and the second and the third, but you do it coherently, which means that you're actually adding up complex signals. So when these complex signals add up coherently in phase, right, you get a gain. When these components don't add up coherently or in a counter phase, they actually cancel themselves. So if you look at what happens when you sum this up at different angles, you end up shaping some sort of beam pattern, okay, that is, it looks like pretty much like a sinc function. I don't know if you're familiar with that. Anyway, we'll do some calculation here. Yeah. So if you square that, you get it's the array factor, which is a power array factor. So you figure out that if you add them up all coherently with theta equal to 0, you get the ball side here, and you get the direction along the ball side. Okay? And then you change theta, looking here this way, and you get all this pattern here, like side lobes. Okay? All right. So if we consider omnidirectional antenna, you are now only considering the array factor. You're not considering the fact that each single antenna has got some gain itself. At the end of the game, once you've obtained this, if you multiply this by the actual antenna gain, right, then you get the total beam pattern, and that's what you're really looking into. But this, see, because it's normalized by the single antenna, it doesn't take into account it. So this is only an array factor. So if we look at the array factor here and you go and calculate it, so first of all, you find an expression of the baseband signal for the generic element, okay, for a generic theta direction. So this particular signal here depends on the distance, or the phase depends on the distance, okay, between the element and the object. So R is the distance, see, at a given angle, right, from a given element down to this point. So this is something that we can write down because we know the geometry perfectly. We are designing our system so that it flies along this direction and with a given distance here. So this RO of I, okay, is actually the distance between this point here, so the central point, okay, of this array, and point O. Now, there's an I, that's it, or if you want, it's a function of I. What's that I? But that I there depends on which range cell we are considering on the ground. We don't want to form an image of only one point, okay, on the ground, but we want to do it for all possible range cells that we are eliminating within our swath. Okay? So this is to say that if I consider the generic and arbitrary range cell on the ground, I define my point O, that works for that particular range cell, but if as I change this value of I, and I say I plus 1, then I move to the next range cell, and then the next again. So this allows me to make this theory valid for all possible range cells. So within my swath, within sort of the minimum range and the maximum range on the ground, I'm able to calculate this distance. Okay? So the geometry, of course, changes at each range cell because this guy changes here. But the signal model doesn't change. Okay? It's only this parameter that changes. So this basically is valid for any of those range cells. So I don't put an I here, okay? But I can say that would make the notation heavier. But I can say that this sigma mod A is valid for any range cell. So what I'm calculating here, basically, okay, is this phase term here, okay, which is the exact value for each of this range here, for every n value. And then I basically go in and approximate this, and you can tell this if you add up this and this basically become this range here, okay, theta, sorry, and 0, which is this one, okay, plus for each particular array, you get an extra bit, right? Maybe I should write it here. So you basically take the central element as a reference element, okay? Which one was, this one as well. So this is the element 0, right? And this, for example, is the element 1. So I take this as a reference element. So I define this as the distance, okay, of theta 0 because this is the element here. So if I want to calculate this, right? Because now I am at a very far distance, so what I'm considering is that the distance here is much greater than this distance here. So now I can assume that these two are almost parallel rays, okay? So if these two are almost parallel, let me write it here now. So I'm taking 0, 1. So now, what I'm considering is that the r theta 1, okay, it will be equal to r theta 0, okay, plus, let's call this d, plus d, and if this is theta, then this is theta, then this bit here is d sine of theta. If I move on, okay, theta like this should be negative, okay, or otherwise I have to put a minus here. But if I choose theta to be positive this way, then it's minus. It depends on how I choose this theta, right? If it's positive that way or this way. Right, so if I do this now, and I do it for all the elements up to the ends, right, then I realize that this is just a multiplication of d, 2d, 3d, up to nd, so I put an n here. So the r theta n will be equal to this plus this term here, right? So this is valid, this approximation is valid when the distance here, r, is much greater than the array extension. This is typically true. Your array is typically much smaller than the distance you're looking at. So if under this assumption, you can actually split this, okay, into this, and this is an almost equal. Right, so if you then write this array factor here, okay, and you do all the calculations, okay, and okay, you basically substitute n with k minus n divided by 2, so you basically shift this from being a sum that goes from minus n divided by 2 to n divided by 2 as a sum that goes from 0 to n, okay? Doesn't matter, it just make a as sort of a circular shift here. So this is easier to calculate because this is a geometrical progression. Right? So you just take the sum, the first, is equal to this q to the power k. So the sum of the first n elements of q to the power k can actually write it in a form like a 1 minus q to the power capital N divided 1 minus q. You know that. Oh, I'll write it here. That's a you know this result is 1 minus q to the power n divided. You know this result. Never seen it before? Sorry. So, well, this is a well-known result. You know, you can demonstrate this. It's the sum of the first power elements of any. And q, of course, must be between, in this particular case, between 0 and 1. Okay. Also, and for this particular case here, we got our q is complex, so it doesn't matter. So if you calculate this, all right, I save all the calculation, you end up with a sine over sine type of expression, and this is the final form of this array factor here. And now, if we look at the particular conditions where theta is much less than 1, and why we're looking at that particular condition. We're looking at that particular condition because I want to remind you that we're trying to look down, okay, here. So theta is going to be very close to 0 if I want to achieve a very fine. So in that condition there, this actually simplifies because now the sine of theta becomes theta, and same here. So if you make that assumption there, then this actually can be rewritten by multiplying and dividing by the same number here. So what you get is n plus 1 down here, so this becomes equal to the argument of the sine, and this becomes a sinc function. So this is interesting because now, close to 0, okay, theta close to 0, then you get a sinc function. A sinc function, we know the properties of sinc function. We know what the resolution of that beam width will be. Okay, and particularly now we can see it here, right? So theta over lambda over 2L becomes the beam width. Okay, if you write this as theta over lambda over 2L, lambda over 2L becomes exactly the first zero of the sinc, which is the sinc beam width. Okay, and that's the array factor here. So, as I was saying before, the minus 3 dB array antenna beam width now becomes lambda divided by 2L. And this explains why you can form a very fine beam.
Sorry, what is L?
L is the footprint of this antenna.
But the assumption is,
Sorry?
are we assuming that's a narrow kind of beam antenna?
This one doesn't have to be narrow at all. Actually, if you pay attention here, like as L increases, so the beam width of the antenna actually increases, the real one. This one decreases. So you get an even finer beam. So this is suggesting somehow that actual smaller antenna buys you more resolution. And why a smaller antenna buys you more resolution? Well, you can see it from here. If you enlarge this beam here, it means that you're forming an array that is even longer. Okay? Imagine this becomes wider, okay? So if this becomes wider, it means that this will be starting from here. This other one will be starting from there. So now your array doesn't go from here to here, but it goes from here to here. Wider array, you get a finer beam. We'll get there because now it's interesting. Like if we look at the azimuth resolution on the ground, so you have to multiply this theta times this distance, right? If you do that, okay, And then, L is actually equal to this product times this, okay? So if you substitute there, you end up with this, you substitute L, right? And then, if you look at the resolution, you substitute this, then you get this divided by this, and what remains is the azimuth size of the antenna. So the azimuth is the actual antenna size along the azimuth divided by 2. That's the resolution you're going to get on the ground. So if I get an antenna of 2 meters, I'm going to get 1 meter resolution on the ground. So this is an incredible result, because now I'm telling you, don't worry about big antennas. Actually, make them smaller. A small antenna buys you better resolution. Ideally, okay, this is all good. Now we'll see what constraints apply to this, so that you will not be able to make it as small as almost zero antenna, almost zero resolution. Well, that doesn't work for a number of reasons that we'll see. But this is not wrong. Within those constraints, this is actually what resolution you get based on the antenna that you put up on the image. It's quite incredible result, isn't it? Well, this is what the array buys you. Okay. Now what we're going to learn next is how to do signal processing, okay, to make that happen. Because let's not forget that we're collecting data as we go. Okay? And in order to understand that, in order to make this processing as simple as possible, we will see a few techniques. But chiefly, the first one would be so-called coherent technique. That technique was actually implemented on the very first sound systems that flew in the 60s. For a very long time. Right. A couple of remarks. So comparing this result against the real aperture. Yeah? So we got now that the azimuth resolution is independent of the range cell distance. Look, there's no dependency in range cell. It doesn't depend on the distance. Whether you're, looking at the 1 kilometer, you're looking at 10 kilometers, you're looking at 700 kilometers from space, that resolution on the ground doesn't change. That's a pretty good result. This is against what was happening for the real aperture radar, where the further back you go, the worse resolution you get. And the second one, as we were noticing before, the azimuth resolution improves when the azimuth antenna size is small. Which is another interesting result. Good. So now we go and look at the coherent integration technique. As I was saying, we want to now look at the signal processing that we need to go through in order to form a SAR image. And we start with this coherent integration technique. So in order to do that, we look at the signal as a radar people, we know it, okay? So we're gonna look at the phases that are related to geometrical parameters, frequencies, and we're gonna look at Doppler frequencies and all the rest. So everything will be familiar from a radar point of view. We will relate all these parameters to geometrical parameters, and then eventually we'll indicate the road that the signal processing to perform to actually form that image, form that beam, pretty much. So let's start with this geometry here. It's the same geometry. We haven't changed the system, of course. The system is exactly the same. It's just looking from a slightly different perspective, from a radar perspective now, rather than an array processing point of view. Right, so we got our platform, okay, that carries the antenna, and it moves same way. It goes from minus t ops divided by 2 to plus t ops divided by 2. So this is the observation time. So I switch on the radar here, switch off the radar there. If I look carefully, this point O will be illuminated from this point all the way to that point. And this point here, unlike the other points that I've indicated as x1, 2, 3, generic xn, right? These points here are not illuminated for the entire observation time. Take it, for example, this x1 here, this is illuminated. As I switch on the radar, this one is illuminated. But as the radar moves along, at some point, okay, this minus 3 dB beam width will actually go beyond this point, and I will assume that that point is not illuminated. It's not really true because the beam pattern doesn't go to 0 abruptly, okay? But it will go to a point where this is not really illuminated enough. So for simplicity, right, let's assume that this is an abrupt, okay, discontinuous beam width, right? Okay, so you can tell that this one is illuminated only for a small portion of this time. This one would be illuminated for a longer portion with respect to this, but less than that. And these are the points on this other side. See, they don't get illuminated right at the beginning. So they have to be waiting until maybe their platform is around here to start illuminating that. So illumination windows, okay, change from point to point. Only point O on the ground is illuminated for that amount of time. Now, I'm going to focus exactly on this point here. And I have as a goal, right, what I want to do is to form an image of this point here. Forming an image, okay, means estimating the reflectivity function of this point here. Because what the radar sees, right, is the reflectivity function of that particular object. It's how much energy gets backscattered by that point. And that's what I have to estimate, because my image eventually will be a composition of pixels, of points that I have estimated, and what I'm going to recognize in that image is going to be the contrast between, one point and another. I will be recognizing shapes if I have a number of pixels in a certain shape that have a different intensity from the background, for example. That's how I recognize objects. My eyes will be tuned to looking into difference in contrast. How do you recognize? I'll show you that image yesterday. There was it wasn't a synthetic aperture, it was a real aperture image of the airport, and there was a tarmac, the runways. Remember? How did you recognize they were runners? Because they were black compared to high intensity. And that's different in contrast, It's something is dark, something is, bright, and you see contours, and you say, oh, look, that looks like a tarmac of a runway. If you look at a lake, within grass or bass, or again, because that's water, that creates some sort of reflection. And you see it darker with respect to this surrounding area, and you say, oh, that's a lake. And you can see the shape of the lake. If you go and look closely, that is composed of a number of pixels, right? And each of these pixels here has got an intensity that has been measured by the radar. So what I'm going to do, I'm going to try and say, okay, this is a pixel in my image, and I want to estimate that reflectivity function of that pixel. And you say, well, only one? No. I'm going to do it for all values of I, for all the range cell. That's going to buy me one strip of range, okay? From the minimum range to the last, which is the maximum range. If I can do it in parallel, I can do it for all this range. And you say, okay, but an image is not just formed by one strip. Okay, that is one strip. But what happens when I move my array by a single step? So instead of starting from here, I start from here, and I finish with one move there. So that means my point always move down here. Yeah? And I can do the same for another strip. And so on, and so forth. So this is to tell you that if I solve the problem for this point O, then I solved it for the whole image. Okay? I'll go back to that later when I talk about strip map. But this is to give you a little bit of preview. So all I'm doing for this point O actually makes sense, because if I can do it for that, I can do it for all the points on it. Fair enough. Now, let's see how I'm going to do that. Okay, I want to measure, estimate if you want, the reflectivity function. And what's the reflectivity function? I call that sigma 0. So the reflectivity function associated with this point O, I call it sigma 0. Okay, that's the amount of energy that it will be, or proportion to the amount of energy that it will be backscattered. Okay, so this point O will generate an echo that will be captured by the antenna at each point here. So if I now write down this signal, as a function of u, and u is this axis here, and a function of I by indicating the ith range cell, then I can see that this particular signal here is composed of this reflectivity function sigma 0, which is an electromagnetic characteristic of that particular scattering. And then the rest will be associated to a phase that changes depending on the distance between point O and any point here, which is indicated by u. U is the coordinate along this axis. And this is going to be lasting in terms of u's, over L, because from here to here we have a distance that is equal to L. And it is centered around 0, so this rectangular function means that I'm going from minus L divided by 2 to L divided by 2. So within this coordinate u, I have a signal, that is defined with spatial coordinates, and this phase turn here depends on the spatial coordinates here. So what I have to do is to find an expression for this phi 0. But this phi 0 here is nothing else but, and you can see it, 4 pi divided by 2 times R0 of u and I. R0 of u and I for any point u, is actually this one. Perfect. And why is it 4 pi? Well, the number 4, it should be a 2 pi times 2 R0, because it's two-way, divided by lambda. You can actually also write F0 divided by C if you want. So that tells you how many rounds the phase does, all the way there and back. It's given by this term. So when it gets back to that point, the phase will stop and we'll have a certain value. That will depend on u and I, because that's a different range. R0 of u and I, you can use Pythagorean theorem here, and it's basically given by this distance squared plus this distance squared and square root of this. So this is the expression, and u is actually this coordinate here, so u squared, is this segment squared. So this is the expression that goes into here. You can also write the same signal model as a function of time. Time and space here are related. Particularly, u, which is space coordinate, is equal to v, the velocity, times t. Alright? That platform moves with a certain velocity, so at a certain time, I will be in a given position. And these two are linearly linked. So now I go u equal to v per t. And you can express this, as a t u, and the slope here is equal to v. So now you got, so you got t that goes from minus t ops divided by 2 and t ops divided by 2, and if you look here, this will be L divided by 2 and minus L divided by 2. So you got this relationship between space and time that is dictated by the velocity of the platform. So now if you substitute u with v times t, then you obtain this other expression here. And the window within which this signal exists now is t ohms. So this is the time expression. And that's a spatial expression. The time expression, all right, again, you have to substitute Vt in place of u, and you get v squared t squared. Okay.
Do you run into issues if there's a major elevation change relative to your, so if you're in a low-flying aircraft, for example, and you're looking at buildings, your L will be changing significantly relative to your.
You fly, or if you fly close,
Yeah.
very, you shouldn't fly too close, because as it will be clear later, the geometry won't be favorable
Yeah.
for you to form images.
Because then your L's no longer.
Well,
constant.
these things are true in far field conditions. So when I said even before, from an array point of view, an array aperture has to be smaller compared to, it's much smaller compared to the distance. So you're flying as a standoff. There are a few cases where so near field SAR actually can become applicable. Those particular cases are not related to remote sensing, they're more related to people have worked, for example, on body scanners. So if you try to use SAR, right, to form a three-dimensional image of the body. I don't know if you've seen some things like those in airports as well. Some work at terahertz, some work actually gigahertz. But those are really niche applications of SAR, and near field SAR is a totally different thing. It should be almost totally separated from this. So this is far field SAR. So what happens to the other scatterers? Because those other scatterers, we shouldn't forget they exist. They're there. So they become, within our problem, where we are interested in this point here, this become a nuisance. And something that is unwanted. Okay? But we have to express the received signal also for them, because what we receive is the sum of all these contributions. This large bin with here collects all the signals from all the scatterers at the same time. So if I write, for example, the received signal for the generic xj, right, and I express it with the same coordinates, right, u and I, for example, then I have an RCS, okay, of sigma j, and the phase that is associated to that point. The rectangular window, okay, that expresses the existence of my signal is actually a little bit different from the one before. Now, this particular scatterer here is only illuminated for a time, okay, that is equal to this delta j, and delta j is expressed here. Okay, and you can write as L divided by 2 plus xj minus, and then you got this minus L divided by 2. So you basically can rewrite this as L minus this absolute value of j, and this is true for both positive and negative. So basically the whole length, you have to subtract this length here to make kind of make sense, right? Also this length. That's the moment where this basically will not be observed any longer. So if you subtract there, and that is valid for both negative and positive value of xj. And this is the central point. So this window has a width and a center. Okay? And the central point, we can calculate it the same sum here. and it's actually xj divided by 2, which would be this point here. So the window would be centered here, and you would have an aperture that is basically L minus this bit here. Okay? So this is a way of expressing the spatial window, so the portion of this virtual array, okay, where this signal that actually exists. That means that for the other portions here, so that's the window, and for these elements here that go from here to here, there's no signal associated. Well, the same can be done also in the time domain. Again, if I substitute u with v times t, I obtain an expression, okay, in terms of time. All right, so this is quite straightforward. So now I've got the expression for all possible scatterers that are present in between this point and that point there in the scene that gets illuminated within this time. So the received signal now will be the sum, right, the superposition of all these components. So in the spatial coordinate domain, I will have the signal that comes off the point 0 and all the others summed up. So this is what I'm interested in. This is some sort of nuisance. And the same I can do it in the time domain. So that's my received signal model. Now I have it. It's a baseband received signal model. There's no frequency f0 anywhere. So this is what I would assume to be the model when I look at my IonQ channels after demodulation. So, coherent radar, IonQ, that's my signal model. Fine. So, here's the assumption again. L is much smaller than the distance. Okay? That's the same condition that we used before the array. Now, if this is true, okay, what I can do, I can approximate this square value, so root square value of the sum of these two square values, right? Can rewrite it like this, and I can truncate this using a Taylor expansion. I can truncate this second order term and ignore all the orders that are superior. Now all the odd order coefficients are 0 because this is an even function. Okay? It's a symmetrical. Being a symmetrical function, all Taylor's coefficient of order 1, 3, 5, all the odd numbers, okay, they're all 0. Whereas all the even numbers, 0, 2, 4, 6, they're not 0. So the next coefficient would be u to the power 4. But we neglect it by considering this expression here. So when this is true, you can stop this at second order. So what we're doing basically, we are approximating this expression here with a second order, sort of parabolic, okay, curve. Right? So if we do that, we come out with this expression here that is true for u, that is less than L divided by 2 in modules, which means we are sticking with this L, which is always much smaller than R0. Good, so in terms of time, same thing, t must be confined within t ops minus and plus t ops divided by 2. So, if I look at the Doppler's frequency, okay, that is generated by point O on the ground, I can find an expression now. And why would I expect that point O to generate a Doppler frequency in LP? Remember the geometry? Point O here. When the platform moves this way, there's some relative radial velocity that is present here. Then this radial velocity gets down to 0 in this point, and then it picks up again and becomes negative. So the platform actually induces a radial velocity. So that signal received by point, is carried by point O, will carry a Doppler component. So what's the expression of this Doppler component? So to calculate this, this should be really cool. I have to differentiate this phase term, okay, and it's the first term associated with point O, and I have to divide it by 2 pi. So that's the definition, okay, of instantaneous frequency. So if I calculate that and I derive that term, okay, I obtain a minus sign here, okay. Minus sign takes into account the fact that targets that are approaching are positive, targets that are receding are negative. Okay? It's convention. So that becomes 2v squared times t, okay, divided by r0 y times lambda. And you can calculate that based on that phase phi 0, which we define somewhere. Phi 0, this one here. Okay? And then you approximate r0 with this term here, and you basically differentiate it. And that's basically this term here, which is 2v squared times t divided by. Okay, so if we then rewrite this in terms of u, then v times t becomes u, so you get this expression here. So you got the time expression and the spatial expression for the Doppler frequency. So now you have an expression for the Doppler frequency. We can go and calculate the maximum Doppler frequency that we are expecting. So my signal, okay, it's important for me to understand what the signal bandwidth here is, right? For a number of reasons we'll see later, it will be clear. But it's important to know when I acquire a signal, even just for sampling purposes, I need to know what the bandwidth of that signal is. So the bandwidth will be generated in this particular case by the maximum Doppler frequency that I can expect. And the maximum Doppler frequency that I can expect is when the platform is in this point or that point. In modulus, okay, they're the same. So here it's positive, here it's negative. But in modulus, the maximum, okay, I can calculate as the maximum value here, and I obtain it when u is equal to L divided by 2, or when t is equal to T ops divided by 2 at the extreme. So if I substitute that, take the modulus, okay, and then that is VL divided by 2, so 2 goes away, then I've got this one. And if I'm careful here, okay, L divided by R0, okay, is practically equal to, for far field, to this theta as, which is the beam of my antenna. If you remember, here, L divided by R is pretty much this angle here. If this is not too wide, now this is a bit exaggerated. In theory, this shouldn't be too wide, and I'll explain to you later. So, as an approximation, if I take it as an approximation, if you want here, rather than a straight equal. But the other interesting thing is that lambda over theta as is actually equal to the as. That's true for antennas. So that tells you that the maximum Doppler frequency is actually related to system parameters only, right? It's related to the velocity of the platform is something that I can design, can control, and the size of my antenna. That dictates the maximum Doppler frequency that I'm going to have. So this is another important result. So the bandwidth of my signal along the Doppler domain is actually dictated by these two parameters. All the other frequencies at any time would be less than that, it's the maximum. So what happens for the other terms, for the other scatterers that are present in the scene? Well, it is interesting to note that what happens for example, this scatterer here, X3, okay? In terms of geometry, what's happening to this scatter here, right, is the same that is happening for scatter in point O after this time here. So basically what's happening is that the platform is moving and is generating this Doppler for point O. The Doppler that is generated for point 3, it will be exactly the same Doppler that is time shifted by this time here. So the time that it takes for the platform to move from here to here. Why not? Why should it be different? You know, they're parallel. What's happening now here is going to happen later there and then there. So there's nothing wrong in writing the expression of the J's R, write it as the R0, where now this R0 is shifted in time by exactly Tj. And this means that the phase that is generated, again, is time shifted. The only thing that I have to account for is that that phase doesn't exist for the entire t-ons, but it only exists for a smaller time, because at some point the radar will be switched off. So that's the only thing that I have to consider, but this term is perfectly fine. So the phase that is generated that depends directly on this guy here is time shifted itself. So it's almost like a deja vu, right? We've seen it for this point, we're going to see it for there, so on and so forth. So if I write the expression for the generic phase here, it's just a simple, because the derivative is linear, right? If I shift my signal, the derivative will be shift the version of the other derivative. So that applies also to the derivative. And if I do that, I rewrite this, and I simply consider the previous version of this one, and I just substitute t with t minus tj. Okay? If I do that, what I obtain is exactly the same frequency that I had before, plus a constant term here. This term is constant. That doesn't depend on t. See? So it's almost like I have shifted up or down my Doppler frequency. So that's a constant frequency shift that depends, it's linearly dependent on this tj. And if I write it in terms of spatial coordinates, now my Doppler frequency will be expressed as in spatial coordinate for point O, and for any other point j, this will be shifted, by this term here, which now depends on xj. It's the same thing. Tj and xj are related, because they're linearly dependent on each other. So what I have to be careful again here is that this signal here exists only in this window, and I explained it. So that tells me where this signal exists, but this tells me what the frequency looks like. So if I want to represent visually my frequency components for all these terms, how am I going to write it down? Well, this comes down to be quite simple. So I take this axis here, time and the instantaneous frequency. If I look at the expression of the frequency, in time for point O, I can see that this, is a minus sign, and these are all positive elements. V squared is positive, R0 is positive, lambda is positive. So I've got a negative here. So that means that I have a negative slope, and the slope is defined by this guy here, and t is my variable. So I've got like a minus a times t, where a is positive. So I've got a negative slope. So if I look at it, and it's a black one, see, it goes from here down to here. This slope here is determined by that particular term. So it's v squared divided by r0 times lambda. Maximum Doppler frequency that I'm going to experience is v over ds, and I calculated that. And that's the maximum, and the minimum is a specular one. So this crosses the 0. I would expect 0 Doppler when this is the 0 point. If you look at this, it goes to, it's a maximum here, goes to 0, and then becomes negative. Here we go. What about the other scatterers? The other scatterers, okay, they will produce exactly the same Doppler, okay, shifted in time. Okay, so these red ones here. But my acquisition window is only confined between minus t ops divided by 2 and t ops divided by 2, which means that the rest of the frequencies only exist within this area. So for example, the frequency that is generated by scatterer x2, which is sitting somewhere, right? It's the generic scatterer 2. It would exist also here, but because the radar wasn't transmitting at this point, you don't see this. So it starts seeing from here, all the way down to here, then it stops. Then it's not illuminated anymore. Scatterers that are on the right hand side start being illuminated afterwards. This one starts being illuminated at this point, goes on, stops here because the radar switches off. If the radar didn't switch off, then it will continue to generate Doppler. Okay, so these are the visual sort of graph that represents basically these equations here. And of course, you can relate this to t, or you can also relate this to u. U is a space, and t is a time. Okay, so space goes from, this is L, and this is t ops. So you can have, either one axis or the other, depending on what's convenient for you. So the Doppler frequency is linearly varying with time, and this is because we have approximated our phase term with a quadratic term. When you differentiate a quadratic term, you get a linear term. That's an approximation, but it's perfectly valid when L is much smaller than R. So that's fine. The maximum Doppler frequency we found out is V over ds. So that's the actual bandwidth. This is a baseband signal, so the bandwidth is calculated like that. And there you go. All right, maximum dwell time for scatterer is T ops and U. So these are the remarks that we're going to use now. So how can we extract the received signal, okay, that is generated by the scatterer in position O? So basically, I want to isolate this because the rest is nuisance, is noise. So if I can isolate this guy here, I can somehow collect, all right, the information about that GPS area. And I'll see now also how then that leads to measuring his reflectivity. So one thing I could do is I could sort of filter this term in this time frequency domain. I could filter this term here, right? By simply cutting off this signal out of there. But to do that in practice, it means that I have to design a filter that changes its central frequency in time, right? So that's mean I should create something that, see, a filter that moves from here to here within that T ops. That's a bit annoying, create a time varying filter. But that's one thing that I can do. I know exactly how this moves. I know exactly how these expressions is like. So why don't I compensate for that term? I can create another signal, a digital signal, right? All this is digital, right? I create this signal here, which is exactly, it's got exactly the same phase expression as that of point O, but it's got a plus sign here rather than a minus sign. So what happens if I take this signal that I generate and I multiply it by the received signal? I can do that. It's a simple multiplication, isn't it? I had my signal, it's a digital signal, right? When I say I got my I and Q channels, it means that I digitize and I have samples of them. And I have this signal that I generated and I multiply them, element by element multiplication. Right? So if I do that, okay, what happens is that my signal becomes a compensated version of my original signal. And I indicate this with C. Okay? This C here means that this is a compensated signal. And I will see why this compensated. In fact, if I look at this and I actually write down the expression and I calculate this multiplication here, okay, what happens is that now for the particular S0 or C, right, what I obtain when I multiply there is this expression here. So this expression contains sigma 0, which is my effectivity function, and a constant phase. This phase doesn't change. It changes with range, but when I fix a particular range cell, this is a simple phase term, which is the phase that I would expect to receive simply because my target sits at a given distance from the ring. But now I can see that this particular signal here, right, contains exactly the information that I need. If I take the absolute value of this, I actually obtain sigma 0, which is what I want. What happens to the rest though? There's also this part of the signals here. So the rest of the signal, okay, if you look at here, okay, I get a constant phase term, all right, and a linear phase, this is constant, and this is a linear phase term that changes according to u. So what happens in terms of graphic visualization is that now my term that was associated with the scalar in point O becomes flat. If you look at this term here, right, that's got zero frequency. This phase is constant. If I differentiate that phase, the Doppler frequency becomes 0. And in fact, I found it at 0 Doppler. Any other scalar, okay, will have a Doppler that is actually associated with its position. And its position here, see, that's the Doppler, for example, for xj, is actually proportional to the Doppler that is generated via this coefficient, which is 2v divided by lambda r0. That coefficient there multiplies the actual position. So that means that a scalar that sits, say, 10 meters away from point 0 will generate a given Doppler frequency. Another scalar that sits 20 meters away from point 0 will generate a Doppler frequency double that. Okay? So you have now a linear relationship between the position of the scalar and the Doppler. The existence of these signals, of course, is still limited here. So this signal here will only last a little bit, this one only a little bit, so on and so forth. And here is the result for the generic one. And that's a result for the scattering zero. So these again are obtained by differentiating this term. So if you differentiate this, okay, this is a constant term. When you differentiate this, you get 0. When you differentiate this, all right, you get this term. U goes away, and you get this term. So that's the basic expression. Okay. So how do we form that image of that point O? Well, now if we sum together, okay, all these contributions here, so the signal that I compensated, which is here, if I now add all the components up, okay, from minus L divided by 2 and L divided by 2, right? Now assume here I've got a continuous value of U, but if this is discretized, and that's the case, you substitute this with a sum. In fact, it comes down here. But in fact, if you integrate this now, you obtain an estimation of this point O, of the sigma point O. Why is this only an estimation? It's not an exact. It's not exact because it would be exact if you only had this term. But because of this, you get some nuisance. But adding up these components, as it will be clear in a moment, okay? Adding up these components here, the other components, actually doesn't create a, what do you call it, a coherent integration, because those terms have a certain frequency. So that means that the phasor changes in time. I'm going to represent this on the whiteboard for you to understand better. It's just an important step. Okay, so let's go back one slide. Look at this. So the received signal, okay, let's put it as a function of t and pi. Okay. So we got sigma 0 times a phase, which is constant. Okay, I just write it like that. And that's a component, okay, sigma 0. So I call this phi 0, okay? It's a constant value. Plus, I have some I equal 1 to n, where n is the total number of scalars, okay? And how do I write that? I write it as sigma j E it's not a function of time, it's actually constant values. And that is that term there, which is 2 b xj okay. This is the expression. What I have is a constant term and a number of terms that are actually complex sinusoids. Because now I have these terms here, or they also have another phase. Let's call it phi j, which is constant. I don't care about that phase. So these terms are this, okay? These are quadratic terms. If you rewrite this as 2 pi and write that as a frequency, Doppler frequency, you can write it like that. It's exactly the same expression, but now you substitute that in there and everything comes out beautiful. You know, the Doppler frequency. You substitute, no, you don't have to substitute anything. This is an expression that you use for the frequency. So what you have here is a constant value and a number of oscillations. Okay, what happens when you take this signal and you integrate it? You integrate this signal, right? Just sum it up. Well, what happens is that constant value stays there. And that gets multiplied by t ops. Okay? Then you get a number of terms. So now the integral and the sum, you can swap to get a sum, okay, over n. And then you get, okay, integral you can put sigma j here. If you want, you can even put e to the j minus j phi e. Okay, that's constant, doesn't depend on t. And then what you get here is e to the minus j 2 pi f dj times d of ft. What you're doing, you are integrating oscillations. What happens when you integrate an oscillation? Well, let's take the real part of that. So you got you integrate this, right? Let's say this is the real part of that expression there. Cosine. When you integrate a cosine within a given interval, what happens? What's the result? Well, you don't know what the result is, but you know that all the complete oscillations cancel out. All of them. First oscillation cancels out because the integral is 0. Second one is 0, 0, 0, 0, 0, 0, 0. You get to the end, there must be some residual. So the only integration you do is on that residual at the end. Right? So that means that the contribution in this integral that is given by these terms is very, very small compared to the other one. It's not 0, I'm not saying it's 0. And for this reason, I can't say that after my integration, I get an exact value of sigma 0. It would be an estimated value. It would be affected by some errors. And these errors would be all these contributions that come from all the other terms whose integrals are really very, very small. Does it make sense? It's almost like you're trying to... Another way of seeing this thing, if you want, is using phasors. To use phasors, right? You know what phasors are? State. So this is, let's say, real part, imaginary part. This is a phasor. Phasor is a rotating vector, all right? So this rotates, and the rotation velocity omega is equal to 2 pi f, where f is the frequency. So any oscillation, any complex oscillation, e to the j 2 pi ft, all right, can be represented by a phasor. The velocity with which this phasor rotates depends on that particular f. So if my f dj, are the Doppler frequency generated by all the other scatterers, those frequencies there are the velocity with which these phasors rotate. Now, let's assume now that you've got a radar and it's sampling those those oscillations every TR. So what you obtain is for the first TR you get this phasor here, then you get this one, and you get that one, and you get that one, that one, that one, that one, so on and so forth. So you see this phasor that rotates, and you sample every TR, and then you add it up. Because you're summing them, right? What's happening? When you sum rotating phases like those. Well, you don't get 0 necessarily, but you don't coherently sum them. If you have a phasor that's got 0 Doppler frequency, that stays in the same position all the time. So this particular guy here, right? Let's assume it's this one. This is here now. After 1 TR, it's there again. And then it's there again, so it sums up. Coherent. The others don't. Okay? But the others don't add up to 0 necessarily. They will add up to some value, which will be, eventually, the result of all these sums will be some vector, small vector compared to all this, coherent sum of the other one. And that will create an error right? It will sum to that one that you want to estimate and create some error. You know, what sort of error? What would be small error? So that's why you don't estimate directly sigma 0, but you estimate something that is affected by small error. And that's the reason why this is not exactly sigma 0. Well, to be honest, here I have to also say that what you actually estimate is not really directly sigma 0. What you're estimating is something that is proportional to sigma 0. Have you ever heard of calibrated radar? Calibrated radars are radars that are able to measure sigma 0, the real RCS of targets. To do that, right, you have to calibrate a radar on known targets of which you know the RCS. And why so? Because the signal strength, right, the received signal strength, is definitely proportional to the RCS, but it's not the RCS. So when I write the expression of the received signal and I write directly sigma 0, well, I'm cheating. Because in front of that, there's a constant value A that depends on the transmitter power, depends on the antenna gain, depends on the target distance, depends on all the losses on my system, blah, 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 propagation losses, atmospheric, whatever, put everything. The radar equation will tell you exactly. If you knew everything of that radar equation, it will tell you exactly what that number will be. But unfortunately, you can't do that. And then there's also noise. So what you're actually coming up with is always an estimation. And it's an estimation of something that's proportional. So that has to be clear. But we do not have to necessarily calibrate our radar and come out with the exact RCS. Because what we're looking at when we're looking at images is the contrast, is the differences. And as long as these differences are preserved, as long as this proportionality is preserved, it doesn't matter if the value is 10 or 15 or 25, as long as that is half of the other value that is the pixel that is adjacent to that, which is 10 or 20 or 20 and 40, doesn't matter. When you visualize it, okay, what you're actually going to see is the contrast. Okay, so that is pretty much how this works. So let's see how we implement this in practice. I told you a little bit how this is actually done, because if I'm actually, you know what, break.
Yes.
Thank you.